sorry, we had some technical difficulties here. I'm going to work on drawing a picture of the derivative of these functions, of this particular function. Now this function is made up of two line segments, or two rays here, I guess, and we have a discontinuity. And so where that discontinuity occurs, my derivative will be undefined. So we're going to have to figure out how to represent that. So you might remember that anytime that there's a line, that the derivative is just equal to the slope of the line. So let me just take a look at this blue portion of the graph. Well, this blue portion, if I just kind of check, this slope goes down 3 every time that we go over. It's kind of tricky here because of the way that the units are. I apologize. It goes down 3 every time we move over 1 unit. So this has a slope of -3. And so for the blue portion of this, the derivative is going to be -3. And so when I'm graphing the derivative, what I'm going to do, maybe I'll call this original function y. My derivative is going to be at a height of -3 for the entire blue portion. Now right here, when x is equal to 1, because of the discontinuity in the original function y, I'm going to have a hole right here in the derivative graph to show that it's undefined right at that instant. Now for the red portion of this graph, let's take a look at the slope. The slope is up 2 every time I go over 1. I apologize, the problem ended up being harder than I wanted it to be because of the way the units were drawn. A little tricky here. I know it looks like up 2 and over 2, but the x coordinates are counting by a half. So this actually has a slope of 2. And so what I'm going to do is I'm going to draw in a height of 2 for the derivative graph. This is y prime. But again, it is not defined right here because of the fact that I have a discontinuity. So this green graph that I've labeled y prime, it's got this kind of looks like almost like a step function here, or piecewise function. This actually would be the graph of my derivative. Well, what if we're not just looking at lines? What if we have a curve? Now we are at this point, we are sketching. We are drawing a sketch. We are not going to be able to draw a super accurate graph from this. We do not have the tools yet. We also do not have maybe enough precise information in order to do a really great job of this. So here's what I want to do. I'm going to draw some tangent lines, and what I'm going to really care about is, are the tangent lines having a positive slope or a negative slope, or maybe even a 0 slope, because that's going to be very helpful for me. All right, if I draw some of these slopes, these are positive numbers, positive slopes. Now this first one I drew is a bigger positive, and then this next positive, the slant, started kind of tabling off until I got to like a slope of like a 0 right here. And then I'm going to continue to have more positive slopes, and these positive slopes are going to be increasing in value. All right, let's see if I can represent this on a graph. So really, if I have a positive slope, then what y prime would be above the x-axis. And a 0 slope would mean y prime has a height of 0. And then a negative slope would mean that y prime is below the x-axis. Now for this particular function, it's continuous. There are no sharp turns, and there's no place where I have a vertical tangent line. So the derivative is going to be defined everywhere, so I'm not going to have any holes in the graph like I did for example 2. I like to graph where the slope is 0 first. Right here, the slope is 0. And so I'm going to have, for my functions, I'll call the original graph y. For the derivative, I'm going to have a height of 0. On the left side, I have these positive heights, or positive slopes, so my derivative is going to be positive. And I'm starting off, when I go from the left towards the origin, this is a steeper slope, and they get less steep, so these slopes start to approach a height of 0, so it looks something like that. And over here, I'm starting off with slopes that are positive but still kind of small, and then the slopes get increasingly larger in a positive direction as I go. So the height needs to be increasingly more positive. Now, when we learn something a little bit more with the power rule, what you'll find out is that there's actually a pretty easy way to graph this. I had mentioned the power rule in the previous video. I'm just going to kind of use it really quickly. It looks like maybe this original function maybe was something like x to the third. If I use the power rule, then the derivative, let's see, I'm just going to go ahead and recognize there's a 1 there. For power rule, you multiply these together and subtract 1 for the power. My derivative graph, y prime, should look like a quadratic, opening upwards, and it does. Okay, now this one's harder to use the power rule on. It's not impossible, but it is a little bit harder. But I'm just going to kind of look again at kind of what I mentioned up here. I'm trying to make a sketch. It does not have to be an accurate graph. Anytime the slope of the tangent line is positive, my output for the derivative will be above the x-axis. If I have a 0 slope, then I'll have a height of 0 for the derivative, and a negative slope of the tangent line will be below the x-axis. I also would like to be watching for where I might have some discontinuities, okay, because those will be if I have a discontinuity, then I have a gap in my derivative graph, because I will not be able to have a derivative defined there. All right, so if I look at these, I've got negative slopes. Negative slopes, negative, 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 negative. Now, as I approach the vertical asymptote for 2, what happens is my negative slopes get more steeply negative. Way over on the left side of the graph, those slopes are negative just barely. In fact, they're actually kind of approaching 0. They're approaching 0, but not quite reaching a slope of 0 because of the horizontal asymptote on this rational function. So what I'm thinking is happening here is I'm getting close to 0 here for my derivative graph, and then I'm getting negative, negative, more steeply negative as I go. Now, where this vertical asymptote is a place where I'm going to be undefined in my derivative graph. So I'll call the original function y, and I'll call this y prime. Looking at the right side, I have a negative, negative, negative slope, still negative, but less negative and kind of approaching a slope of 0. Something like this. I'm thinking that there's probably a vertical asymptote right in here. Now, you might feel very uncomfortable with this idea of graphing the derivatives right now. That's very normal, and you will get better at it, okay? So don't panic. We are going to be writing equations of normal lines, and normal is a term you've not heard before. It's very related to a tangent line. A normal line is going to just be perpendicular to a tangent line. And so because it's perpendicular to it, it uses its slope, the normal slope, is the opposite reciprocal of the tangent line slope. And the tangent line slope, keep in mind, is the derivative. So to find the slope of a normal line, it is going to be the opposite reciprocal of the derivative. In a previous video, we actually did example 5 with a tangent line. Now we're using a normal line. Well, we're still writing an equation of a line. And when you write an equation of a line, you need a point and you need a slope. So to find the point, the ordered pair, they already gave me the input here of 2. I just have to find the output. To find the output, use the original function and substitute in the input, and you'll find out that the output is 3. To find the slope, I'm going to find the tangent slope first. The tangent slope would be the derivative. I'm going to use this power rule again. So I'm going to take the power and multiply it by the constant in the front, and then subtract 1 from the power. And then for this one, I have x to the power of 0, and so when I multiply that out front, I just get a 0. That's x to the power of 1 right here. It's not x prime. And so the tangent line specifically at 2, this is still working with the tangent line. The tangent line at 2 would be 2 times 2, which is 4. So the slope of the normal line would be the opposite reciprocal of this. which would be -1/4. When we write the equation of a line, I'm going to use HK form, where the ordered pair is HK and the slope of the normal line is M. I'm just going to substitute my M in x minus the x coordinate and then plus the y coordinate. And there is the slope of the tangent line, or the equation of the normal line, pardon me. And that is the end of 3.2 notes.